As the slide suggests, the title is about differential equations and inclusions indeed of monotone type. For the solution of this kind of differential inclusions, usually a semigroup will be generated. Today, we will discuss the existent results about this kind of differential inclusions and equations indeed. And we will see that how they generate a semigroup and how a semigroup is connected with the solution of a differential inclusion or equation. First, we recall the definition of a non-expansive semigroup. A non-expansive semigroup is a family of mappings from a subset. Here we consider Banach spaces, but it can be Hilbert space or any other spaces with several properties. First is that S of 0 be the identity mapping. And they have the property of a semigroup in the sense that S of T plus S as two elements of positive real numbers be the composition of S of T and S of S, and you see that this means that they are commutative. And the third one is that this mapping from the positive real numbers to T of Tx for a fixed S x, this mapping be continuous with the usual topology that we have for R and the norm topology for the Banach space. And the final one is that these mappings need to be non-expansive in this sense. S of T of X minus S of T of Y less than the norm of X minus Y for all X and Y in C and for all T. You see that Grandal and Liggett proved the first nonlinear version of the Hille theorem in Banach spaces. I first recall the Hille theorem here. It is a linear form of the Cauchy problem that we will consider today. Let A be a single valued mapping from X to X. X is a Banach space. And assume that this A is closed in the sense that if Xn converges to X and Yn converges to Y, and if A of Xn is Yn, then A of X equals Y. And assume that the domain is dense in X, and also I plus lambda A inverse. Assume that this one is defined on X, entire X, and we have this inequality. Then Hille showed that this limit exists, the limit of I plus lambda A over minus n, this lambda b t over n splitter. And if you take this u of t, then he also showed that exactly on any x of x, exactly, so this one exists, and u is a solution to this Cauchy problem. This is a linear Cauchy problem that has this form that exactly this form, u prime, but for the single valued, u prime of t plus a u of t is 0, and with this initial condition, where x here is an element in the domain of A. You see that in the previous slide here, Crandall and Liggett shows that for any Banach space, there is no condition and assumption on that Banach space. And for any accretive A in X times A, and for any X in the closure of the A. Here you see that this theorem first proves for X in the domain, and this one, it doesn't show that here, that it is a solution of any differential equation or any other thing. Just it says that the limit of this limit, I plus tna minus 1, the same as Hille theorem. This one exists, and this is the resolvent that in previous session we saw, Jn t over nx, and if you call this one st of x, they also showed that S of t is a non-expansive semigroup. Indeed, this exponential formula generates a non-expansive semigroup. Now the question is that, is it possible to show that this exponential formula is a solution of the Cauchy problem, the nonlinear one, this problem? You know that the solution of this one, if there exists a solution, generates a semigroup. I mean, if this Cauchy problem, when A is a, for example, we may assume just it is accretive. And as we assume that there is a solution for this one, then this solution has any relation to non-expansive semigroups. We write S tilde of T x be defined like U of T here, and I do some calculation here to show that S tilde is also a semigroup, and it is indeed a non-expansive semigroup. So we have just assumed this problem has a solution, and now we want to generate a semigroup. The first thing is that we show that the solution, if there exists one, is unique. So for the uniqueness, it is easy to apply the accretivity of A and write this easy calculations. Assume that U1 and U2 be two solutions, and in the sense that U1 prime of T belongs to A U of T almost everywhere by this minus, because it corresponds to the Hille theorem, and assume that we have this one, U of 0 is X is fixed, the initial condition for this solution, and also assume that we have for the second one the same condition, and I write this one for I 1 and 2, and by the accretivity we may write U1 prime of T minus U2 prime of T and J of U1 T minus U2 T. You know that from the assumptions that we have, this one belongs to minus A U1, and this one belongs to minus A U2. And you know that the definition of accretivity is this, that Y1 minus Y2 and J of X minus X1 minus A2 is greater than or equal to 0, and for all X1 and Y1 in A and X2 and Y2 in A. In view of this definition, you see that this one, because it has minus, it's less than 0. And from this one, we deduce. I remind you about the derivative of this function, 1 over 2. D on D of dt, U1 of T minus U2 of T to the 2 equals to U1 of T minus by prime, the derivative, and J of, if it is single valued or not, equals to here J of U1 T minus U2T. I will explain this equation and why it is differentiable, and we can write this in the next slides. But if you consider this one and this one, we deduce it is equal to equals exactly 1/2 dt, the normal U1 minus U2. And to the 2. And we see that this one is less than 0. And so we deduce that since we have this one, we deduce that this mapping U1T minus U2T is non-increasing. And so by using the continuity of the solutions and writing after taking limit on the right side, we have U1 0 minus U2 0, and this one is 0 because the initial condition is that U1 and U2 on 0 are x, and so we deduce that U1 equals U2, and so the solution is unique. As you see here, we have just used the accretivity, and we have not mentioned any accretivity or any other assumptions. There is a similar argument that shows this S tilde, this one, S tilde is a semigroup. And if we show this, we have generated a semigroup from a solution. We define S tilde of x be uxt. And uxt is the solution. I have changed the notation here. Ux is the solution of the Cauchy problem with the initial condition that u of 0 is x. We have defined this one. We also can assume that x here is an element of the closure, because here we have assumed that this problem has a solution for this elements of the closure of A, but we may also write x in D of A and then using the continuity. So we have such x, and we need to show that it is non-expensive. The tilde of t is non-expensive. So we consider x1 and x2 in the domain, the closure of domain, and we use again of this result and we write ux1 of t minus ux2 of t. Here we have chosen two elements in the closure of the domain. And we want to show that S tilde t x1 minus S tilde t x2 minus its norm is less than the norm of x1 minus x2. This is our aim, and we may write like before this one as u x1 prime minus u x2 prime and j of u x1 of t minus u x2 of t. And you see that this one belongs to minus a u x1 of t, and this one minus a u x2 of t. By the accretivity, we see that this one is less than 0. Accretivity. So there is a there is no question. Since we have this one, we deduce that this mapping, the mapping from T to ux1 of t minus ux2 of t to the 2. This one is non-increasing because its derivative is negative, and so this one is non-increasing. And from this, the norm of ux1 of t minus ux2 of t less than ux1 of 0 minus ux2 of 0, which is x1 minus x2. And here, by this notation, we may write S tilde t of x1, and for this, S tilde t of x2. This shows that S tilde of t for any t is non-expensive. And the final thing that we need to show is that this S tilde has the property of the main property of a semigroup, which I write it. Here, we need to show that S of, for example, two scalars in R. I use, for example, T and tau. We need to show that this equality holds. For this, we consider some x in the domain of A closure, and let x tau, we define x tau like S of S tau of x. And we also define u1 of t be S tilde t plus tau of x and u2 of t s tilde of t of s tilde of tau of x. And we can define this u1 and u2 because we have a solution since we assume this one. And the second one is exactly x tau. We see that u2 is a solution to the problem with this initial point, u2 of 0, with the initial condition u2 of 0 be the point x tau. It's easy to check because we have here a differential inclusion that the coefficients are constants and it is homogeneous. I will explain this reason later for other results. So this one is a solution and u2 is a solution with the initial condition u1, I mean, u1 of 0 equals to here u1 of 0 is s tilde of 0 plus tau, and it is s tilde tau x, which is x tau. So both of the initial conditions are the same in this case, and both of them are solutions of the problem, since we have shown that the problem has a unique solution by the accretivity. We reduce that by the uniqueness. We see that u1 equals u2. So if they are equal together, then we reduce that. S tilde t plus tau of x equals s tilde t and its composition to s tilde tau, which is the main property of a semigroup. So we have generated a semigroup. I review again the next slide, the previous slide here. By Crandall and Liggett, we have generated here a semigroup. This semigroup, ST of X. It is generated through the exponential formula, this exponential formula. The argument is different from the semigroup we have generated on the board. And the next slide, it says that if this Cauchy problem has a solution, even if A is only accretive, then we can generate a semigroup. So it is natural to ask, is there any connection between these two semigroups? And the other question is that, is it possible to show that the previous one, the semigroup generated by Crandall and Liggett, is indeed a solution for the Cauchy problem, as that Hille showed in his theorem for the linear case and single-valued one. We know that in general Banach spaces, this problem is not solvable, even if we assume A is M-accretive. And Crandall and Liggett have presented an example to show that. But in the general Banach spaces, the issue is different if we assume, for example, X is reflexive, as we will see in the next slides. They have proved a result which is interesting. You see here that if A is an accretive, I'm not sure that you see this here, and if X is an element of the domain, not in the closure of the domain. With these assumptions, they have shown this by implication. They have shown that if U is a strong solution of 1 for X in the domain, then their exponential formula is indeed exists, this limit exists, and equals to the solution. So if U is a solution, then we deduce that their exponential limit equals to that solution. Indeed, this result was first proved by Brezis and Pazzi, and Crandall and Liggett showed the converse one, that if is a strong solution, then this solution can be written in the form of an exponential formula. And the converse is that if U be taken as this limit, we know that this limit exists for M-accretive operators, and if it is strongly differentiable almost everywhere in addition, then we deduce that U is a solution of the Cauchy problem. So this exponential formula is not necessarily a solution, but in the case that it is strongly differentiable, then it is a solution of the Cauchy problem. It is interesting. So from this result, we deduce that for the case that X is an element of the domain of X, this semigroup that generated by Crandall and Liggett, we wrote as S of t, and the semigroup that is generated by the solution of a Cauchy problem are the same. But under some limitations, that if the Cauchy problem have a solution and X be an element in the domain, not in the closure, which is more general. But it is So interesting. And so we see here that the semigroup that here is generated is can be written as a limit, and it has a representation as an exponential formula. Here, I remind you the definition of strong solution. A strong solution here is that it is absolutely continuous and differentiable almost everywhere, both of them. And we say that U is strongly differentiable almost everywhere. For the part that we had here, UT is strongly differentiable almost everywhere, is that it is absolutely continuous and almost everywhere differentiable. You may have seen in some books that an absolutely continuous function is almost everywhere differentiable. It is not the case in the general case. But for the reflexive Banach spaces and Banach spaces that satisfy some properties, we have this implication. I remind the definition here of absolutely continuous and x-valued function U defined on an interval like A and B here is said to be absolutely continuous if we have this inequality, the sum of n from n to n, U of Tn minus U of Sn less than epsilon. And also for every epsilon, there exists some delta of epsilon that this one holds whenever we have the sum of n from 1 to n, the absolute value of Tn minus Sn be less than delta of epsilon. And for the aim of that this definition be well defined, we assume that these intersections be empty. This segment we assume has no intersection, because if we remove this one from the definition, we may repeat some segments several times and the definition will be undefined. So it is the definition of an absolutely continuous function. But which kind of functions are absolutely continuous? For example, we see that K-Lipschitzian functions are absolutely continuous. It is easy to show that if we take delta of epsilon be epsilon over K for the constant of the Lipschitz function, then we obtain the implication that we have in the definition of the absolutely continuous function. It is important to know that if we have four real valued functions, that an absolutely continuous function is differentiable almost everywhere. But for the vector valued function, we don't have this property, and the spaces that have this has this property is called they have Radon-Nikodym property, and we have this result from Komura states that a reflexive Banach space has radon-Nikodym property. And we reduce that in that spaces. Every absolutely continuous function is almost everywhere differential. So if X is reflexive, then we may just write the result mentioned as this: S of t is always strongly differentiable everywhere. Since S of t, we show that it is non-expansive. S of t is non-expansive, so it is absolutely continuous. And if the space is reflexive, it is differentiable almost everywhere. So we have that from the Crandall and Liggett result that we may, in the space of that reflexive, that their exponential formula always generate a solution for the Cauchy problem when X is an element in the domain of A. I recall this result again. If X is a Banach space and A is accretive, then for any X in the closure of the A, they have shown that this limit exists and generates a non-expansive semigroup. And as mentioned, this one, in the case that X is an element of the A, is a solution. And there is a question here. Is the converse of this statement here false? This question asked by Cato indeed this year, the year that this paper indeed was published. There is a result in the Banach space case. There are some results in the Hilbert spaces, but I mentioned because we are going to present everything in Banach spaces. This is a nice result due to Reich, which says that if we answer that question, it is a nonlinear form of the Hille-Yoshida theorem. And Reich asked this in some certain spaces that they are enough general because they include Hilbert spaces and many other Banach spaces. This is the result that Reich proved. Let C be a closed convex subset of a uniformly convex Banach space with a uniformly Gauss differentiable norm. Then, for any non-expansive semigroup, the converse of the theorem proved by Crandall and Liggett is that they generated from when A is accretive, they generated a semigroup. There exists a semigroup. The converse is that if we have a semigroup, like a non-expansive semigroup, assume from C to C, is there A which is accretive and S of t can be generated through the, I like this, right, the definition of the exponential formula. Is there an A that represent S by this limit. Here, I remind you the definition of K lambda, which is I plus lambda A, inverse we saw in the previous session. So this question answered for this case that the space is uniformly convex with a uniformly Gauss differentiable mode. For these spaces, in the last result I wrote on the board, we saw that the domain of A in that case is always closed and convex. So we may reduce the question to the case that C is closed and convex. So the answer is this: if we have a non-expansive semigroup S on C, where C is closed and convex in this space, then there exists a unique accretive A such that C is the closure of the domain, and it generates S via the exponential formula. It is interesting because we can have a good understand from the structure of this kind of semigroup by using this exponential formula. And moreover, we show that the infinitesimal generator of S is minus A0. We saw the definition of 0, and I will recall again. For X in A, we show this equation. The limit here, you see that is similar to taking a derivative here, indeed, from S of t at the point 0, which is minus A0. And it is interesting, but it is still an open problem because finding more general Banach spaces having this property is interesting. And there is another thing. If you can generate a semigroup from other ways, like generating from the second order differential equations, then you can generate or obtain an accretive that semigroup can be represented by this one. I will explain again, because this one first used to by Barbault to get a notion to define the square root of a maximal monotone operator in the Hilbert spaces. And I will explain this one later. As I mentioned, A0 is the element of the minimum norm on A of X. A of X is a set, and the space is uniformly convex, and it is reflexive. And A of X, you saw that is convex and closed. So it has a minimum. It has a point with the minimum, and it is unique by these assumptions. And so it is A0 of X is indeed the projection of the 0 onto this set. As mentioned, if we solve a second order differential equation and generate a semigroup, we can relate it to the finding of an accretive operator, and we may represent it by the exponential formula. I explained this interesting result. Pufald and Reich in this year established the existence of solution to this problem. This problem is interesting. You see that it is the second derivative of u, which belongs to a of u, with this initial condition. You see here a second order differential equation, but the assumption here is the initial assumption is that just u of 0. We don't have any assumption here for u prime, because normally you see that for solution of the second order differential equation, we need to have two initial assumptions, one for u, for example, this one, and one for u prime. And under these initial conditions, sometimes it's possible to solve a differential equation. Here you see that instead of the second one, it is assumed that the solution be bounded. So the boundedness here is added instead of this one. Also, as mentioned in the title, we are working on here in this presentation, monotone type mappings. So the monotone and this property together are indeed here instead of this, the second one, the u prime of 0, y. So they proved that this second order differential inclusion has a unique solution. Here we see that x is an element of D of A. If we show that this problem has a solution for x in the closure of A, it's an extension for this result. The assumptions is that A is an accretive operator. 0 is normal to have this assumption. In the range, we need to have 0. And the space is uniformly spaced. And the duality mapping is here strongly monotone. Strongly monotone duality mappings you remember the definition of the duality mapping is the element of E star such that the normal x equals the normal x star and x star of x is the normal x2. And we saw that they always is monotone. Strongly monotone is different if we have some fixed m here. That this term from this left term is greater than m x minus 1 to the power of 2 for all x and y, then we say that the duality mapping is strongly monotone, and strongly monotone include the Hilbert spaces, L2 spaces for LP spaces for P between 1 and 2, and some other Banach spaces. They prove the existence of a unique solution, which is continuous here and it is differentiable, and the derivative and the second derivative belongs to L2. Under this condition, there are properties that will be obtained from the proof, and uniqueness is under these assumptions. There is a unique solution under these assumptions. I remind some other results concerning this problem, because first time this problem investigated by Barbu, and he used this one in Hilbert spaces for finding the square roots of the operator A. And I here remind you that if you solve this problem, this will generate a non-expensive semigroup. And a non-expensive semigroup generate or correspond to some A that with the exponential formula equal generates the semigroup. And by this way, they define that A as the square root. So as you see here, we may have several differential equations of, that generate semigroups, and also so we cannot obtain a square root that is unique. We may have several by this notion, and in this sense we have several square roots. So it is interesting if you have a more general differential equation to generate the semigroup and then obtain the root from that. If you have a more general differential inclusion, then you will have and you will be able to obtain a better definition for the square root of the operator A. I remind some other results concerning this one because there is no assumption here that u prime of 0 is y, and it is interesting because without this assumption, the uniqueness is proved, and but Brack and Pfeffert and Reich called it as an incomplete Cauchy problem for the lack of this assumption. But under the boundedness and other things, the uniqueness is obtained. And also they worked on this problem on the form of the non-homogeneous case that U double stop belongs to AU of T plus F of T. It can be a general, more general form of the Reich and Pfeffert equation and the sup of U of T less than infinity, but they have not shown the in a general form the existence of the solution for this one, because it has no solution in the general case if you don't have any assumption on the function f here for the non-homogeneous case. Even for the case that a is 0, this problem has no solution because the second derivative of a function should be exactly F in this case. And so at least F should have the second derivative. But they prove an interesting result concerning this one. They show that if there exists a solution for this one, the non-homogeneous case, then for some, I mean, if there exists some x in the domain, the closure of the domain, such that the problem, I call it star, has a solution, then for all y in the domain of A, star has a indeed unique solution. Here, by using the equativity, we obtain a unique solution, a unique solution. This problem also proved by Braque in the general real, indeed, in the Hilbert spaces. And it was studied by Reich and Shafrir in general Banach spaces, but for the case that A here is the Yoshida approximation of A, and A lambda, the Yoshida approximation is single valued. Indeed, the problem for this case, but for general Banach spaces, they didn't assume any kind of uniform convexity, smoothness, and anything. It's a nice result, I think. And there are some other papers also on this issue. And the point is that we need some assumptions on if that cause the problem having a solution. And one of the results that I mentioned here is the result that presented by Morosano in 2014. He solved this general form of the inclusion equation. And here you see that you have P of t here as a function, Q of t. So you have U prime in your differential equation, and you have F of t, and X is in the closure of the domain. But for the Hilbert spaces, and it is a nice result, we generate a semigroup for the case that F is 0, and the coefficients are constant, because we can generate a semigroup just in these cases. But it is a general form to generate a semigroup, and then by using this, defining a better definition, a better concept for the square root of the operator A here. So in the case of Banach spaces, we studied this problem. Indeed, Karisa Jamshidnejad and I studied this problem in the Banach spaces, and under the same assumptions that Reich and Pruwald made. First, I remind some notions and definitions. Let I be an open interval in R, the real numbers, and X be a Banach space. For P between 1 and infinity, the Sobolev space, W1P, is defined as the elements of P such that there exists some G in LP such that this equality holds. And what is this equality? As you see here, it is like the integrating by parts that you have here. U phi prime equals minus G phi. And G has the role of the derivative of U. We have not mentioned anything about here the differentiability of U, but we consider some elements in LP that there exists G with this property corresponding to the integrating by part formula. And this holds for all phi in CC, 1 of I, which is the mapping with compact support. They are continuous and differentiable, continuously differentiable. And there is a question here. I see. You have reached the record limit. So it should be mentioned here that this U is called in Sobolev spaces the derivative of U. This G is called the derivative of U, this G, in the sense of distribution. But what's the relation between this notion of the derivative and the usual one? So from now on, we use U prime as the derivative in the sense of Sobolev spaces or in the sense of distribution. And we may define a norm of this space like this. U be the norm of U plus the norm of U prime, which is the Banach space by this norm. And it is known the connection between the absolutely continuous functions and the elements of Sobolev spaces is this one. For any U in this Sobolev space, there exists an absolutely continuous x-valued function U tilde in C, the closed interval AB, and X the vector valued, such that they are equal almost everywhere in this segment. And also the derivative, the real derivative of U tilde, you know that absolutely valued, absolutely continuous functions are differentiable almost everywhere. That's if derivative equals to the derivative in the distribution sense that's defined above, almost everywhere. And so for the Sobolev spaces, always we may assume that the elements are absolutely continuous. And also it is possible to define the Sobolev space W instead of 1 and P, M and P by induction. Indeed, W and P is the elements in W, M minus 1 and P, such that its derivative in both notions, distribution or the usual one, be in the previous one, W M minus 1P. And this example is interesting, and it's clear something about the solution of the differential equation on unbounded domains. It's the absolute value T, which is an element of WP because you have the derivative as this one, and U and its derivative are in LP in this notion. But for the second derivative, U prime has this form. The question now is that you saw that for the elements of Sobolev spaces, always we may find continuous function, even absolutely continuous function, that they are almost everywhere equal to the function. If we have this function here, like G, is it possible to find a continuous function which is equal to G almost everywhere? I try. Is it possible? No, they are not. And if we near this curve, anytime near to this line, I cannot find a continuous one. So there exists no continuous F such that G equals F almost everywhere. You may try. If you find one, write to me. This problem will be explained later. So we deduce that U prime here, this U prime, is not an element of a Sobolev space, since there is no continuous function which is almost everywhere equal to this one. And U is not so, it is U, the absolute value function is an element of the Sobolev space, but you see that it is in the Sobolev space 1 and P, but it is not in W 2 and P. So they are different. There is a result that we saw on the board, that if X is a reflexive Banach space and U is an absolutely continuous function, then U of t is differentiable almost everywhere, and its derivative belongs to L1, and we have this form. It is a vital equation for studying this kind of differential equation in the Banach spaces. And Catu's theorem is interesting. Also, let X be a Banach space, the general Banach space here, and U be a weakly differentiable with weak derivative u prime by this definition. The weak definition of the differentiability is that d of u of t for any f in x star, this one exists. And then we deduce that we have this equality that we used it for any f in j of u of x. This lemma is important. I will explain its importance. Let X be a smooth and reflexive Banach space. So J is single valued, and it is a space that absolutely continuous functions are almost everywhere differentiable. Assume that the vector value u is continuously differentiable and u prime absolutely continuous. Then this function q of t, u prime of t, j u of t, has interesting properties. The first one is that q of t is differentiable almost everywhere. You may think that it is trivial that it is differentiable because u prime is absolutely continuous and q has this form. I write here the definition of q, and q of t is u prime of t and j of u of t in the smooth space. We may think about, is it the second derivative of u of t? The answer is not. We cannot remove a prime here for adding another one to u prime, because we had just this result. If you think from this one can obtain the above, it is not the case. We have this one. But this doesn't imply the above. And we need to use other techniques to show that it is differentiable almost everywhere. But we cannot show this equality. Fortunately, Reich and Kofal presented some inequalities that are useful and we can use instead of using this one. One of them is this one, the integral of the q prime. In the A part, they show that q is differentiable almost everywhere. And the second one shows that the integral is less than q of t minus q of s, and they are not equal. And necessarily, it doesn't say that they are equal. This part C is interesting because you see here that q prime, we know that q prime is not the u double prime of the j u of t, but we have this interesting inequality. The norm of u to the power of 2q prime of t is greater than the norm of u of t to the power of 2 u double prime j u t plus 1/2 q to the 2 of t almost everywhere. And we may use this one instead thinking about this kind of questions. And also there is another interesting inequality in the case that J is strongly monotone with the constant that I explained here. We have this interesting inequality Q prime of T is greater than U double prime of T, Ju plus M, the norm of U prime to the 2. Here, the part C proved by Reich and Schiffer, and the other parts proved by Hofald and Reich. Here, I mentioned a remark that Q prime here is not an element of L1. We know that we have this inequality, but it is not an element of L1. Why? Because we don't know anything about the U of T for any 0 and T, for example. If we add absolute value here, we don't know that it is less than infinity or not. This is the question. An example to be convinced about this is an alpha, which is non-decreasing function, and it is known that for such functions, the functions that are non-decreasing, they are differentiable from R to R almost everywhere. And we have this inequality for such functions. Integral from A to B, the derivative of alpha is less than alpha of B minus alpha of A. And we have also that from this one, alpha and its derivative belongs to L1. Because here, the function is non-decreasing. It's not general. Q here may be decreasing or not. We have no idea about it. However, there are increasing continuous functions. If you think that continuous increasing functions may be elements of the Sobolev space, you may see this example. A Cantor-Levy function, if you search on the Google definition, is continuous and increasing, but it's not absolutely continuous. This shows that the derivative of the Cantor-Levy function is not derivative in the sense of distribution, as mentioned. And it is not an element of the Sobolev space W11. But we may check that the Cantor-Levy and its derivative are elements in L1. Even both of them be in L1, it doesn't imply that it's be an element. It is an element in the Sobolev space. And in which, by adding other conditions, we may obtain that such functions are in the Sobolev space. For example, if U is an element of C1, C1 is the continuous function that their derivative are continuous. But for this one, the Cantor-Levy function, we know that its derivative is not continuous. This lemma proved by Hofald and Reich, but we needed it without the assumption that B here be monotone. They proved this under the condition that B should be mandatory. And this lemma is interesting for people who are working in these equations. Let P, Q, and H be continuous and assume that the first one is non-zero and assume that P, H, their multiplications are positive. Then there are two solutions, phi and psi, of this equation. Is a second order, typical in this second order differential equation in the real line, and it's not vector value. And the solution has these properties. This solution, if phi and psi are solution, we may write this A and B and C. We use that result to obtain this lemma, Jamshid, Nujad, and me. X be a smooth Banach space with a strongly Manhattan duality mapping. Assume that P and Q are continuous function with essential inf of P greater than 0, and F be an element of L2, then this second order differential equation P of T, U double prime plus Q of T, U prime minus U equals F of T, with the boundary conditions U of 0 equals X, U of T equals Y, has a unique solution in W22. Uniqueness under this assumptions that U be an element of W22 circular space. And you may think about the case that is it possible to have solutions from this one? Assume that we have, for example, P of T, U double prime of T plus Q of T, U prime of T minus U of T equals F of T. Instead of 0 and T, we may write this one for all T greater than 0. The first idea is that if we consider here the simple case of the real valued functions, think that we have solved and obtained a curve from 0 to 1. So it is possible by this result. By this result, we may obtain for any bounded intervals. And from here, with the initial conditions between 1 and 2, another one. And also another one. And is it possible to deduce from this procedure to have a solution for all the positive real numbers? The answer is negative, because we have here the solution in W22. And you see here, we have some points that we may not have a derivative here. And the other part is that we usually use this one and we don't know how to define this sequence to continue, to make it as a base and continue the procedure. And the important part is that usually we want to obtain such solutions under some boundedness. we want to have our solution in the unbounded domain for the T when we have this condition. So by this procedure, we may obtain a solution which is not bounded. Assume that P and Q are continuous from now on, and the essential inf of P be greater than 0 as before. We define EW, the weighted spaces. This is the tools that we need to present the main results. L2R over P be defined as this, L2R. This is a weighted space indeed. Instead of D of T, we have RT over P of T. They are the coefficients that are functions in the problem that we are going to solve. And R of T is defined here, e to the power of the integral from 0 to T, Q of T over P of S, and X is assumed from now on a smooth Banach space. And EW is assumed here, the Banach space that induced by this norm. This should be less than infinity, the integral from 0 to infinity, R of T over P, the norm of U of T to the 2. And we denote is the duality mapping. For that mapping, the duality mapping is calculated as this U and JEWB like this. The integral from 0 to infinity R of T over P of T, U of T, J, B of T. This is the duality mapping of the original Banach space, and this one is for this weighted space. Let A here be an accretive operator in X. We define this A from a domain in the space that defined in the previous slide, this one. And the domain is defined here as the elements of EW, such that U of T is an element of the A and B is, there exists a B in EW with this property. B of T is an element of A, U of T. This kind of operators are called realizations of the set-valued mapping, because here A is multi-valued, and we use this kind of operators to choose some good elements of the multi-valued operator A, which are suitable for finding the solution. And A is an element here such that it is in the domain of A, and B of T is an element of U of T. You see that here the new functions, the new operators have curves in their as elements of their domain, and it is useful to work and obtain the solution. You know that for an accretive mapping, one of interesting things is that the domain, the range is the complete, the entire space E. If we use a realization of A, then we obtain a curve is space of curves. So for any curve in the space that is extended, we may represent it in terms of the realization operator A. And if A is an accretive operator with this property, and A is accretive, then we may, this A is accretive. So under this condition, A is accretive and 0 in A of 0, then the realization of A is accretive. This assumption is not an extra one, because we had in the assumptions for all of the result that 0 is an element of the range, and using a simple method that I mentioned, we by transferring the domain, we can assume that 0 is an element of A0. And we may use these notations as the Yoshida approximation of this curved domain A and the original A respectively. And we have these equalities, they are easy to show. We may define a similar one for the bounded intervals. And for the bounded interval, we see that we have this equality that L2 0t with this weight algebraically and topologically are the same, but from the viewpoint of the geometry, they are not the same. And the norm can be defined like this. We also define another operator from the space of the curves by this one, U in the space of curves, such that U prime and U double prime be an element of the space also. And we have this initial condition. You saw this initial condition in the lemma that I mentioned there, and it's here. And B is defined like this. It is exactly the form that you see here. By using this and using the M accretivity of B, we and if this differential equation has a solution, we can show that B indeed is M accretive. It's important. For B M accretivity, to be M accretive, we need to apply this result. And we have this interesting lemma. This lemma proved first by Morsano as a key result for his result. And he used another method for obtaining this one. In the Hilbert space, Morsano showed that B is indeed the subdifferential of an operator, which is convex lower semi-continuous. And the method here is different. The proof for the Banach space case, as you know, the notion of subdifferential in Banach space is different. And you have subdifferential as a subset of X star. But for the Hilbert spaces, you have subdifferentials from the Hilbert space to Hilbert space. So we had to use this procedure For the proof, I mentioned the proof to see how it is used in this proof. We first note that every function u and C2 satisfies this one, belongs to this, so D is non-empty. Let U and V be elements of the domain of B, and B of U minus B of V and J of U minus V can be written as an integral, as shown by the property that J had here. This one. So we may write this as this one by the definition of B, because B defined like this, and we write it as this one. We rearrange it and write a prime for all of the, and R has a form of the exponential, and using that, we have this one, and we distributed the prime, and for this inequality, you know that we want to transfer one of the primes to out of the term, and you know that we cannot do this for the this form of J. We have had just for the norm of 2, the norm to the power of 2, and to use this one, we applied here the part 4 of the Reich and Pfalz lemma as an inequality, and we may rearrange again like this by this inequality. We had also this one minus R U prime minus V like this, which is greater than this one you saw as Q and R. I mentioned that R not the B in that lemma is general, and using that lemma and the property of Q, we obtain this one, and we may write as this. So B is accretive. To show that B is inaccretive, we need to show this equality holds. And we let some element in this space, and we must find an element in the domain of B such that that element plus an element of B of that element equals to F. For doing this, we just need to have this one. And this one has a solution, because we proved in a lemma the solution of this second order differential equation is the solution of this equation. So B is inaccretive. And for solving the main problem, we need to first solve the case that this problem has solution on the segment 0 and t, and using some procedures that I have not included the proofs here. If we prove this one, and using this is the reason that why we can assume that 0 is a element of A0. And we obtain this theorem for the bounded case in the case that we have a segment 0t. The mentioned problem, this problem, E prime and B prime, has a unique solution in the case that A is equative and P is an element of this distributive space and Q is a continuous function and F also is an element of this distributive space. Then for all X and Y in D of A, there exists a unique solution satisfying the conditions that we want. And by the proof, using the procedure of the proof, we also may extract this one, which is important. So as mentioned, for solving the differential inclusions, we usually use the Yoshida approximations because Yoshida approximations are single valued, and as mentioned in the last session, we have properties like this one, which is, and since A0 of X, using these properties, it is better to work with differential inclusions. And this is the assumptions that we need for to state the main result. P be an element of distributive space, P0 be the essential infinite and greater than 0, Q be an element of L infinity, intersection C R plus, the continuous function, and bounded here, Q plus B an element of L1, which is defined as usual. And we use these definitions L1 of 0x with this weight By and R minus T be defined like this for simplicity. And Y be the real Banach space with respect to this norm. And we know that from this assumption, some easy inequalities, and there is not enough time to explain why these inequalities are important from the viewpoint of the assumptions that we made and the comparing between the several assumptions. And what is the definition of a solution in this? For first, LP log Jx is defined like this. All x-valued functions defined on J. J is a subset of R, is an interval in whose restriction to the compact intervals belongs to LP. It's called LP log, and we may define the distributive space by log in this way, similarly. And this definition, F be an element of W log 1, 2, and X be an element of the closure of D of A, then an X valued U of T is said to be a strong solution. This is the definitions that we have used for the solution. We have strong solution and weak solution. Strong solution is that U be continuous, be in the distributive space, and satisfies the assumptions of the problem, the second order differential inclusion problem. And we have a definition for the weak solution, indeed, if we have a sequence of solutions on the compact intervals that converges to our solutions, then we say that it is a weak solution. In this, if n converges to f, un satisfies the equation and this, and un uniformly converges to u on compact intervals. So under this is a main result under the assumptions that mentioned. If X is an element of the closure of D of A, and F is an element of Y intersection this Sobolev space, there exists a unique strong solution to the second order differential inclusion with that general form, such that it is bounded in this way, in this sense. And we have also that the derivative and second derivative are also in L2 with these weights, and in the time is going to be finished. If X is an element of the domain, then we obtain a better result here. U, in this case, is in this Sobolev space, insists of this one. This is log. And this one, the left side is closed. This one is open. It is important because it's full, just in the case that X is an element of dA, the domain, not in the closure of dA. And for the same assumptions, if X is an element of dA and Y in just Y, it's more general, then there exists a unique, there's a unique weak solution in this case, because F is more general here compared to the previous one. And under this assumption, Q is the coefficient of the U prime. If it's in L1, then we obtain this boundedness. And even for the homogeneous case, here we have eliminated F. Then in this case, we obtain by a new procedure and using the previous one indeed, that we have better assumptions for the solution here, because here we have the norm of U of t decreasing in this case. And it is important to create a semigroup from the solution. And also we may obtain, because the time is over, for the weak solution under weaker conditions. I don't mention that. Let's consider the general case by using the same method that I mentioned, because here we have some inequalities inside the proof. I have eliminated them, but using S of t of x like this one, as I explained on the board, and for all x in the closure of d of a, we may obtain this inequality, but it is not a semigroup property. It is just an inequality. It is about non-expansiveness, and there's some inequalities that is in the proof. And if we have the homogeneous case, it is possible to create a semigroup, but here it is important. The coefficients should be constant, because without that, we are not able to create a semigroup. It's possible just in these cases. And the semigroup is new because it's a semigroup that is generated from a more general form of the second order differential inclusion. And by using this, we may define a square root, which is better and more general for the operator A. And this is the proof of this. And there are some applications that I threw it away very quickly. For example, if we assume X is LK, this space and this assumptions, then this wave equation has a unique solution using our results, and also the solution is for this one. Under this one, we obtain weak solution if we just assume F is in Y, like this, and here is assume that this form this one. Yes, here F is in L1. So we obtain a weak solution. There is another result that we may state for the strong solution. And here we have this one. And this is a homogeneous case. And I mentioned some of the references. That's all, and thank you.